Hello everybody and welcome to the first lecture in Electrical Engineering Fundamentals. The concepts and principles covered here will be used not only for the remainder of this course, but in other courses related to circuit design and electronics. In this lecture we will cover the following: voltage, current and power, circuit schematic and ideal basic circuit elements, independent and dependent voltage and current sources, Ohm's law, Kirchhoff's current law and Kirchhoff's voltage law. We will further illustrate all of these concepts by solving several examples and problems containing independent and dependent sources. We will begin by defining the voltage, current, and power. The voltage is the energy per unit charge created by the separation of charges. The voltage can be expressed in differential format as V equals to dW over dQ, where V is the voltage in volts, W is the energy in joules, and Q is the charge in coulombs. The current is the rate of charge flow and is given by I equals to dQ over dt, where I is the current in amperes, Q is the charge in coulombs, and T is the time in seconds. The power is defined as the energy per unit of time, or it is the time rate of generating or absorbing energy. The power is given by the following equation: P equals to dW over dt, where P is the power in watts, W is the energy in joules, and T is the time in seconds. The power can also be associated with the current flowing through the terminals of a circuit element and the voltage across these terminals, where P equals to VI. If the power of a circuit element was positive, it means that this element is absorbing or dissipating power. A negative power, on the other hand, indicates that the element is generating or delivering power. In order to correctly calculate the power of a circuit element, we need to follow the convention illustrated here. If the current is flowing through the terminals of the element in the direction of voltage drop, then the power equation is written as P equals to VI. This is the case shown in the first and second figures, where the current is flowing from the higher voltage level, indicated by the positive sign, to the lower voltage level, indicated by the negative sign. If the current is flowing inside the element in the direction of voltage rise across its terminals, then the power equation is written as P equals to minus VI, as shown in the third and fourth figures. After writing the correct equation for the power, we need to substitute the values obtained for the voltage and current with their corresponding signs, whether it was a positive or negative voltage or positive or negative current. If the power was positive, it means that it was absorbed. If the power was negative, it means that it was generated or delivered. In this example and for the circuit element shown, V equals to 5 volts and I is equal to 10 amps. In part A, we need to calculate the power delivered by the element. In part B, we need to calculate the power absorbed by this element. The first step in calculating the power, as was explained in the previous slide, is to check the direction of current flow with respect to the voltage across the terminals of the element. Since the current is flowing in the direction of voltage rise, then the power equation is written as P equals to minus VI, which gives that the power is equal to minus 50 watts. Since the power is negative, it means that it's being delivered by this element. So, in our answer for part A, we write that the power delivered by the element is equal to 50 watts. Note that the word delivered eliminates the need for the negative sign. Our answer for part B would be that the power dissipated by the element is equal to minus 50 watts. The negative sign indicates that the power is being delivered, not dissipated. Now we will talk about the second part of this lecture. A circuit schematic is a diagram representing a set of interconnected circuit elements where each element in the schematic is presented by a symbol. The lines connecting the symbols in the schematic can be considered as wires with zero resistance. An ideal basic circuit element like the one shown in the figure has three main attributes. The first attribute is that it has only two terminals. The second one is that it is described mathematically in terms of current and voltage. The third attribute is that it cannot be divided into other elements. From here on, and as was illustrated in the power equation, and will be illustrated in the following slides, we will be using the passive sign convention in our analysis. In the passive sign convention, a positive sign will be used in any expression relating voltage to current when the current is flowing in the element in the direction of the voltage drop across its terminals. Otherwise, we'll use a negative sign. There are five ideal basic circuit elements: the voltage source, the current source, the resistor, the capacitor, and the inductor. Voltage and current sources are considered electrical sources. An electrical source is a device capable of converting non-electric energy to electric energy and vice versa. For example, a discharging battery converts chemical energy to electrical energy. When it's being charged, it converts electrical energy to chemical energy. Now we will take a closer look at voltage and current sources. The figure on the left presents the symbol of an ideal voltage source. An ideal voltage source is a circuit element which maintains a specific voltage across its terminals, regardless of the current flowing through these terminals. The figure on the right presents the symbol of an ideal current source, which maintains a specific current, regardless of the voltage across its terminals. An independent source like the independent voltage and current sources presented in figures A and B establishes a voltage or a current without relying on voltages or currents elsewhere in the circuit. A dependent source, on the other hand, establishes a current or a voltage whose value depends on the value of a voltage or a current elsewhere in the circuit. Dependent sources are also referred to as controlled sources. These are the ones presented in figure C to F. In figure C, we have an ideal dependent voltage controlled voltage source, where the generated voltage Vs is controlled by the voltage Vx. In figure D, we have an ideal dependent current controlled voltage source, where the generated voltage Vs is controlled by the current Ix. In figure E, we have an ideal dependent voltage controlled current source, where the generated current Is is controlled by the voltage Vx. In figure F, we have an ideal dependent current controlled current source, where the generated current Is is controlled by the current Ix. Please note that circles are used to represent the symbols for independent sources, and diamonds are used to represent the symbols for dependent sources. Now we'll talk about Ohm's law, or the electrical resistance. The resistance of an element is the opposition to the flow of current through that element. The figure in the middle of the slide presents the symbol of the electrical resistance R. The relationship between the voltage and current at the terminals of a resistance is shown in the figure to the right, where the positive slope V over I is the resistance R. Following the passive sign convention, and as illustrated in the two figures at the bottom of the slide, V equals to IR when the current is flowing in the direction of voltage drop. V equals to minus IR when the current is flowing in the direction of voltage rise. The equation V equals to IR or R equals to V over I is known as Ohm's law, after George Simon Ohm, a German physicist who established its validity in the 19th centuries. The resistance R is measured in ohms, which is presented by the Greek letter omega. The reciprocal of the resistance is referred to as the conductance, which has the symbol J, where J equals to I over V or 1 over R, and is measured in Siemens. The resistance converts a portion of the electrical energy to thermal energy. Hence, the resistance is always absorbing power, where the power P equals to I squared R or V squared over R. Now we will talk about the most important section of this lecture, which is Kirchhoff's current and voltage laws. However, before explaining Kirchhoff's current law, we need to understand the meaning of the node. A node is a point where two or more circuit elements connect. The figure on the left presents a node connecting three circuit elements. The figure on the right presents a node where 6 elements meet. Kirchhoff's current law, also known as KCL, states that the algebraic sum of all the currents at any node in a circuit equals to 0. Kirchhoff's current law can be expressed mathematically as the summation of the currents leaving a node is equal to the summation of the currents entering that node, or the summation of the currents leaving a node minus the summation of the currents entering a node is equal to 0. In other words, what goes in must come out. Conventionally, a current leaving a node is assigned a positive sign, and a current entering a node is given a negative sign. For example, applying KCL at node A in the first figure, and noting that I1 is entering node A and I2 is getting out of node A, we get minus I1 plus I2 equals to 0, or I1 equals to I2. When the same current flows in two elements, and these elements are connected in series, which is the case between R1 and R2 in this figure. Applying KCL at node B in the second figure, we get minus I1 minus I2 plus I3 minus I4 plus I5 plus I6 minus I7 equals to 0. Before introducing Kirchhoff's voltage law, we need to understand the meaning of a loop. A loop is a closed path starting at a selected node and returning to the original node without passing through any intermediate node twice. As illustrated in this schematic, we can identify 3 loops. Loop 1 consists of V0, V1, V2, and V3. Loop 2 consists of V2, V4, V5, and V6. Loop 3 consists of V0, V1, V4, V5, V6, and V3. Kirchhoff's voltage law, also known as KVL, states that the algebraic sum of all voltages around any closed path in a circuit is equal to 0. KVL can be expressed mathematically as the summation of voltage drops across the loop equals to the summation of voltage rises, or the summation of voltage drops minus the summation of voltage rises equals to 0. In other words, what goes up must come down. Conventionally through the loop, and as illustrated in the figure, a voltage drop is assigned a positive sign and a voltage rise is assigned a negative sign. For this circuit, applying KVL on loop 1, we get minus V0 plus V1 plus V2 minus V3 equals to 0. Applying KVL on loop 2, we get minus V2 minus V4 plus V5 plus V6 equals to 0. And applying KVL on loop 3, we get minus V0 plus V1 minus V4 plus V5 plus V6 minus V3 equals to 0. The best way to understand Kirchhoff's laws and Ohm's law is through examples. In part A of example 1, we need to use KCL, KVL, and Ohm's law to find I0. In part B, we need to verify the accuracy of our answer by showing that the total generated power is equal to the total power dissipated. We begin by assigning a current to the 50 ohm resistor as shown in the schematic. Call it I1. We also assign a voltage across the 10 ohm resistor. Call it V0. Since we have two unknown currents, I0 and I1, we must derive two simultaneous equations involving I0 and I1. We obtain one of these equations by applying Kirchhoff's current law to either node B or C, summing the currents at node B and assigning a positive sign to the currents leaving the node gives minus I0 minus 6 plus I1 equals to 0, or I1 equals to I0 plus 6. This is the first equation. We obtain the second equation from Kirchhoff's voltage law in combination with Ohm's law. Noting from Ohm's law that V0 is equal to 10 I0 and V1 is equal to 50 I1, we sum the voltages around loop 1 to obtain minus 120 plus V0 plus V1 equals to 0, or minus 120 plus 10 I0 plus 50 I1 equals to 0. This is the second equation. In writing this equation, we have assigned a positive sign to voltage drops in the direction of the loop. Solving these two equations for I0 and I1 yields I0 equals to minus 3 amps, I1 equals to 3 amps. In part B, the power dissipated in the 10 ohm resistor is equal to I0 squared times 10, which equals to 90 watts. The power dissipated in the 50 ohm resistor is equal to I1 squared times 50, which equals to 450 watts. The current in the independent voltage source is flowing in the direction of voltage rise. Hence, the power in the independent voltage source is written as P equals to minus VI, which equals to minus 120 I0, which equals to 360 watts. Since the power is positive, it means that the independent voltage source is dissipating power. The current in the independent current source is flowing in the direction of voltage rise of V1. Hence, the power of the independent current source is written as P equals to minus VI, which equals to minus 6 V1, which equals to minus 900 watts. Since the power is negative, it means that the independent current source is delivering power. The total power dissipated is equal to 90 plus 450 plus 360, which equals to 900 watts, which is equal to the delivered power. In example 2, we need to find I3, V1, V2, V3, and the total power delivered by the voltage source. We begin by noting that all the elements in the schematic are connected in series. This means that the same current, I3, flows in all of these elements. Applying KVL on this loop and assigning a positive sign to voltage drops in the direction of the loop, and noting from Ohm's law that V2 equals to 2I3, V3 equals to 5I3, and V1 equals to minus 1 times I3, we obtain minus 24 plus V2 plus V3 minus V1 equals to 0, or minus 24 plus 2I3 plus 5I3 plus I3 equals to 0, which leads to I3 equals to 3 amps. From Ohm's law, we find that V1 equals to minus I3 times 1, which equals to minus 3 volts. V2 equals to I3 times 2, which equals to 6 volts, and V3 equals to I3 times 5, which equals to 15 volts. The current I3 is flowing in the direction of the voltage rise across the independent voltage source. Hence, the power equation is written as P equals to minus 24 times I3, which equals to minus 72 watts. However, in our answer, we will write that the power delivered by the voltage source is equal to 72 watts. Notice that we don't put the negative sign, since the word delivered eliminates the need for the negative sign. In example 3, we need to find R using Ohm's law and Kirchhoff's laws. We begin by assigning a current to the resistor R, call it I1, a current to the 20 ohm resistor, call it I2, and a current through the 5 ohm resistor, call it I3. We can find the value of I2 by applying Ohm's law, where I2 equals to 100 over 20 equals to 5 amps. Applying KCL at node A and assigning a positive sign to currents leaving the node gives I3 equals to I1 minus I2 equals to I1 minus 5. Applying KVL on loop 1 and assigning a positive sign to voltage drops in the direction of the loop, we obtain minus 150 plus I1R plus 100 equals to 0. Applying KVL on loop 2, we get minus 100 plus 5I3 equals to 0, from which I1 equals to 25 amps. Substituting this result in equation 3 leads to R equals to 2 ohms. In solution B to example 3, the only difference here is that, unlike the case in solution A, the direction of loop 2 is counterclockwise. All the equations will be the same as the ones obtained from solution A, except for the equation derived from applying KVL to loop 2. Changing the direction of the loop will result in the same equation, but multiplied by a factor of -1. Since voltage drops in the clockwise direction are now voltage rises in the counterclockwise direction. However, changing the direction of the loop doesn't affect our answer. R is still equal to 2 ohms. In this section of the lecture, we will solve examples with independent and dependent sources. The same basic principles apply, except here, in order to find the voltage or current generated by the dependent source, we need to find the controlling current or voltage. In part A of example 4, we will use Kirchhoff's laws and Ohm's law to find V0. In part B, we will show that the total power generated is equal to the total power dissipated. Looking at this circuit, we find that there are two closed paths, the one on the left with current Is and the one on the right with current I0. In order to find V0, we need to find I0, since V0 equals to 3I0. Applying KVL on loop 1 and assigning a positive sign to voltage drops in the direction of the loop, we obtain minus 10 plus 6 Is equals to 0, which leads to Is equals to 1.67 amps. Applying KVL on loop 2, we get minus 3Is plus 2I0 plus 3I0 equals to 0, which leads to I0 equals to 1 amps and V0 equals to 3 volts. The power dissipated in the 6 ohm resistor equals to Is squared times 6, which equals to 16.67 watts. The power dissipated in the 2 ohm resistor equals to I0 squared times 2, which equals to 2 watts. The power dissipated in the 3 ohm resistor equals to I0 squared times 3, which equals to 3 watts. We notice that the current Is is flowing in the direction of voltage rise across the terminals of the independent voltage source. The power equation is written as P equals to minus 10 Is, which equals to minus 16.67 watts. The negative sign of the power indicates that the independent voltage source is delivering power. The current I0 is also flowing in the direction of voltage rise across the terminals of the dependent voltage source. The power equation is written as P equals to minus 3Is times I0, which equals to minus 5 watts. The negative sign for the power indicates that the dependent source is also generating power. Adding total power dissipated and total power generated verifies that they are equal to each other. In example 5, we need to find I1 and V. We start by assigning a current to the 500 ohm resistor, call it I. Applying Kirchhoff's current law at node A and assigning a positive sign to currents leaving the node, we get minus I1 plus I minus 40 I1 equals to 0, or I equals to 41 I1. Applying KVL to loop 1 and assigning a positive sign to voltage drops in the direction of the loop, we obtain minus 3 plus 29.5 times 10 to the power 3 I1 plus 0.5 plus 500 times 41 I1 equals to 0, which leads to I1 equals to 50 microamps. Applying KVL to loop 2, we obtain minus V minus 2.4 times 10 to the power 3 times 40 I1 plus 10 V minus 500 times 41 I1 equals to 0, from which V equals to 4.175 volts. In example 6, if I3 equals to 5 amps, find Vs, the power absorbed by the independent voltage source, the power delivered by the independent current source, the power delivered by the controlled current source, and the total power dissipated and absorbed. We begin by assigning a current to the independent voltage source, call it I1. A current to the 5 ohm resistor, call it I2, and a current to the 10 ohm resistor, call it I3. We also assign a voltage across the dependent current source, call it Vy, and a voltage across the independent current source, call it Vx. By applying KCL at node A and assigning a positive sign to currents leaving the node, we get I1 equals to I2 plus 6I3. Applying KCL at node B, we obtain I2 plus 6I3, which is the current entering the node from the dependent current source, equals to I3 plus 5, which is the current leaving the node and is generated from the independent current source. Noting that I3 is given and is equal to 5 amp, and that I2 plus 6I3 equals to I1, we get that I1 equals to 10 amps. From the first equation, I2 equals to I1 minus 6I3, which equals to minus 20 amps. Applying KVL on loop 1 and assigning a positive sign to voltage drops in the direction of the loop, we get Vs plus 5I2 plus 10I3 equals to 0, which leads to Vs equals to 50 volts. Since the current in the independent voltage source is flowing in the direction of voltage drops across its terminals, then the power equation P is equal to Vs times I1, which equals to 500 watts. Since the power is positive, it means that it's a dissipated power. The current of the independent current source is flowing in the direction of voltage drop of Vx. Hence, the power equation is written as P equals to 5 times Vx, which equals to 5 times 10 I3, which equals to 250 watts. Since the power is positive, it is absorbed. However, since the question was about delivered power, our answer should be that the power delivered by the independent current source is equal to minus 250 watts. The current of the dependent voltage source is flowing in the direction of the voltage drop of Vy. Hence, the power equation is written as P equals to 6I3 times Vy, which equals to minus 3000 watts. Since the power is negative, it means that it's being delivered or generated. Our answer should be that the power delivered by the controlled current source is equal to 3000 watts. The power dissipated in the 5 ohm resistor equals to I2 squared times 5, which equals to 2000 watts. The power dissipated in the 10 ohm resistor is equal to I3 squared times 10, which equals to 250 watts. Total power dissipated equals to 500 plus 250 plus 2000 plus 250, which equals to 3000 watts, which is equal to the total power delivered. Before concluding this chapter, we will solve a couple of problems to further illustrate the concepts. In problem 1, we need to find I2, I1, and I0. Start by assigning a current through the independent voltage source, call it I. Applying Kirchhoff's current law at node A and assigning a positive sign to currents leaving the node, we get I minus I2 equals to 0, which leads to I2 equals to 0. Applying KVL to the first loop and assigning a positive sign to voltage drops in the direction of the loop, we obtain minus 24 plus 2I plus 10I equals to 0, which gives I equals to 2 amps and V equals to 20 volts. Applying KVL to loop 2, we get minus 20I1 plus 5I0 equals to 0. Applying KCL at node B and assigning a positive sign to currents leaving the node, we obtain 0.8 V plus I1 plus I0 equals to 0, which leads to I1 plus I0 equals to minus 16 amps. Solving equations 1 and 2 leads to the result that I0 equals to minus 12.8 amps and I1 equals to minus 3.2 amps. In problem 2, we need to find I delta and V0. We need also to show that the total power generated is equal to the total power absorbed. Applying KVL on loop 1 and assigning a positive voltage to voltage drops in the direction of the loop, we get minus 50 minus 20 IS plus 18 I delta equals to 0. Applying KVL on loop 2, we obtain minus 18 I delta plus 5 IS plus 40 IS equals to 0. Solving equations 1 and 2, we get IS equals to 2 amps, I delta equals to 5 amp, and V0 equals to 80 volts. To calculate the power of the first and second dependent voltage sources, we need to find the current flowing in each of them. We assign I1 and I2 as illustrated in the schematic. Applying KCL at node B and assigning positive sign for currents leaving the node, we get I2 equals to IS plus 8I delta, which equals to 42 amps. Applying KCL at node A, we obtain I1 equals to I2 plus I delta, which equals to 47 amps. The power dissipated in the 18 ohm resistor is equal to 18 I delta square, which equals to 450 watts. The power dissipated in the 40 ohm resistor is equal to 40 IS squared, which equals to 160 watts. Since the current in the independent voltage source of 50 volts is flowing in the direction of voltage rise, the power equation is written as P equals to minus 50 I1, which equals to minus 2350 watts. Since the power is negative, it means that it's being delivered or generated. The current in the first dependent voltage source is also flowing in the direction of voltage rise. The power equation is written as P equals to minus 20 IS times I1, which equals to minus 1880 watts. The negative power indicates that it's being delivered or generated. The current in the second dependent voltage source is flowing in the direction of voltage drop. Hence, the power equation is written as P equals to 5 IS times I2, which equals to 420 watts. A positive power means that it's being dissipated. The current in the second independent voltage source is flowing in the direction of voltage drop. Hence, the power equation P is written as 8 I delta times 20, which equals to 800 watts, and the power is being dissipated. In order to find the power of the 8 I delta dependent current source, we need to find the voltage across it. Applying KVL on loop 3, we obtain V plus 20 minus 40 IS equals to 0, which leads to V equals to 60 volts. P equals to 8I delta times 60, which equals to 2400 watts, and the power is being dissipated. The total power dissipated is equal to 4230 watts, which is equal to the total power delivered. As I mentioned in the beginning, this is the most important lecture not only for this course, but for other electrical engineering courses. If some of the points covered here are not clear, or if you have any question, don't hesitate and contact me. Thank you.